Welcome back to the lab. We have set out on a mission to end fires caused by 3D printers once and for all. That is why we are designing, building, testing, and sharing Seth, an electronic device which detects thermal runaway and cuts mains power to a 3D printer reliably when an overtemperature fault occurs. That's right, friends. Today we're going to share the theory of operation for this circuit and explain how component failures were considered to guarantee fault tolerance. Oh yeah, I'm excited. I hope you are too, because this design is pretty cool and I'm excited to share it with you. By the way, the schematic is linked in the description below. Check it out if that helps you follow along. To keep this as straightforward as possible, let's look at one of the thermocouple inputs and one of the mains outputs. There's duplication of these circuits to provide the second thermocouple input and switch both sides of mains, but the form and analysis is identical between the upper and lower halves of this design, and I suppose there's a couple of resistor and maybe a couple capacitor value changes, but the signals flow from left to right on the schematic page, and we're starting at the top left. Now that's hard. Basically, there's 4 configurable resistor dividers where you can change the switch position to set one of the 4 temperature thresholds. We've designed this circuit such that 4 different levels that can be selected are 76, 95, 139, or 200 degrees Celsius for the heated bed. There's 4 microfarads of bulk on this net to, first of all, help the system to start up predictably, more on that later, but also to ride through the brief moment when the switch is moving between states and there's no resistor connected from 5 volts to the top of the divider. If you change the switch position and it just immediately locks out the printer, that might not be the best way to go. These capacitors effectively allow for changing the voltage threshold without worrying about tripping the monitor. Kind of a niche use case, but that's a real situation that will happen sometimes, like if you're changing print materials. And anyways, there's a comparator and some provisions to protect against faults here, but we'll circle back to that in a moment. We're in theory of operation land right now, where all of our components are constrained in performance, as described by the tolerances listed in their respective datasheets. So, we have a selectable voltage threshold. Great! Now what? Well, as suggested by the thermocouple datasheet, I added the external 1 mega ohm pull-down and RC network that provides some additional ESD hardening for the AD8495. This should, therefore, provide a reliable 5 millivolts per degree C output voltage. This output voltage is directly compared with the threshold set as VBED, and the MIC7221 open collector comparator pulls the OK net down to ground if the thermocouple voltage rises above the trip threshold. If the bed thermocouple is unplugged, thermbed, that net called thermbed, becomes 5 volts, which will always trip the comparator, asserting the not OK state. That should work fine, but we need a pull-up resistor on that OK net, which, man, it is really hard to show you everything at once. But I suppose you may be wondering exactly where that resistor is. Great question. There it is. Yep. A 10K resistor pulled up to 5 volts with an LED that is illuminated if any comparator is tugging on the OK net. Great. Whenever we are not OK or the OK net is pulled to ground, we begin charging or discharging depending on if it's on the... Well, you get the point. We basically start charging a bunch of bulk capacitors that total around 8 microfarads. We're doing that through a 23 kilo ohm resistor, and this causes the OK filter net to transition from around 4.7 volts to about 2.5 volts in a nominal time of 100 milliseconds. That's on trip time. The temperature comparators need to hold a not OK state for about 100 milliseconds. Doing so triggers Seth to turn off power to the 3D printer. This is the glitch rejection we've been talking about, that 100 milliseconds delay between, hey, there might be a problem, and oh yeah, there's a problem, turn it off. This is where things get extra fun. If OK filter drops below the 2.5 volt threshold, then the final comparator will trip, turning off the NPN transistor, which turns off the PFET, which turns off the relay. Basically, we're holding a normally open relay closed all the time until we trip. Now, this was an important design decision because failure modes. We'll get to that in a second. Once U7, the final gatekeeper, recognizes that OK filter dropped below 2.5 volts, it pulls down on that OK filter net, causing it to stick on forever until power is removed from Seth. Basically, this design requires a hard power cycle to reset. There's no reset button, there's no switch. You gotta unplug it, physically plug it back in to restore power to the printer. As long as there's power applied to Seth, it will never unlatch. Alright, I've been itching to dive into the failure modes of this design, so let's get into it. Hopefully you enjoyed that run through of how this design functions. To summarize what we just talked about, basically comparators, voltage division, and resistor capacitor time constants is how the temperature monitor works. But what about when stuff breaks? What about when things misbehave? How can we make sure this design will really actually work if little things like manufacturing errors happen? I'm so glad you asked. Fault tolerance time! Yeah! Let's do this. The closer a fault gets to the relay, the higher risk it is, the more impact a single component failure will have on the system. This is especially true of the relay itself. Relays typically fail in two states, either welded shut or permanently open. If our relay fails open, no problem. The 3D printer won't power on or burn down the shop, and it'll be pretty obvious that something is broken. If a relay fails short, the relay coil has no effect on the system, and your 3D printer will be on all the time. That sounds like a problem. I guess we might need two relays in series. Now, either relay can fail as a short circuit, and we can trust that the other one will open reliably. We'll use one relay to break line and the other to break neutral. That way there is absolutely no power being delivered to the printer in a no-fault condition. Only earth ground remains connected after a fault. Sweet. Now we have two relays, but should we control them with one MOSFET or two MOSFETs? Well, I decided to implement two discrete MOSFETs because MOSFETs can also fail either open or shorted, and the relay control FET failing short will cause the control circuit to have no control of the relay coil, and this is the same reason why we're building the temperature monitor in the first place, because we can't trust the MOSFET controlling the heated bed inside our 3D printer to not fail into the always-on shorted state. To allow a user to detect this fault more easily, a visual indicator was added to display whenever power is applied to either relay coil. The two relay state indicator LEDs should always be in the same state, and the LED state will tell you whether the relays are in the correct state by checking the conductivity compared with the LED being on or not. If something doesn't line up, the monitor is broken and must be serviced or replaced. To mitigate single fault conditions that compromise the safety of this design in a pretty critical way, we've decided to duplicate everything, including the relays, back through to the comparator that's making the decision to turn this off and latch itself. But should we use one comparator to evaluate whether to turn off the printer? Well, maybe, but I chose not to. I duplicated this comparator because if it fails to control the relay effectively, either due to a short circuit fault in R30, an open circuit fault in R37, or a failure to latch due to an open circuit fault in R28 or D2, the duplication of a second comparator will make extra double super sure that if OK Filt ever drops below the 2.5 volt threshold, the 3D printer will turn off and stay off. If one comparator latches OK Filt to less than 2.5 volts, that means it will hold the other comparator in the correct state too. So there could even be a minor circuit defect and you wouldn't even know. Yep, so from OK Filt down to the relay, we are pretty darn sure that the system will operate correctly. There are basically two redundant copies of the same circuit to, by nature, establish single fault tolerance. One whole circuit could be depopulated and it would still work. Now, here's where things start to get a little tricky. As I evaluated faults from the other direction, the things that cause OK Filt to move, duplication here gets expensive quickly. For example, any of the timer capacitors could fail short, latching OK Filt to 5 volts hard, and therefore never trip. Likewise, R18 or R19 could fail short, R20 could fail open, the comparators comparing the threshold and current temperature could fail to change state. The thermocouple monitor IC itself could malfunction and output 0 volts forever. These are real scenarios that could happen, but they can also be periodically tested, and they're not very likely. To make sure the device isn't damaged, periodic testing seems like a pretty good idea. And just because we can't mitigate every single fault with built-in provisions and hardware, I still built in some features that protect against the most likely failure modes. For example, a thermocouple getting unplugged or failing as an open circuit due to repeated bending, because it's on a 3D printer. In either of those two states, the thermocouple monitor will output 5 volts, which will cause both relays to open about 100 milliseconds because it's basically reporting 1,000 degrees Celsius. To make sure all those components are still operational, anyone can measure the resistance on the relay outputs, and we can unplug each thermocouple one at a time to make sure that both circuits are still functioning. We can then take the hot air gun and heat up the thermocouple to test the trip thresholds and verify accuracy. We can push the switch into all 4 states to check for open and short circuit faults in both ranges, and really, this circuit is just sitting on a shelf, being there. It's probably going to be fine. The big reason why I decided to not duplicate the thermocouple monitors is because if this isn't good enough, if you want more fault tolerance than one thermocouple front end can provide, then use 2 Seths. Put 2 of these devices in series and wire them such that if either one trips, then both line and neutral will be broken. There's nothing preventing a person from putting 2 of these thermocouple monitors in series to become truly 2 fault tolerant, but implementing this level of fault tolerance on one board would result in nearly doubling the already skyrocketing price tag of this design. However, we do monitor the threshold voltage divider for overvoltage faults, where setting the threshold too high causes the relays to turn off. This mitigates short circuit faults in the 4 programming resistors, and I think that's pretty good too. Regular maintenance seems like an acceptable resolution to some of those nuanced single faults in comparators or the temperature monitor I see. That's partly because we don't have a good way of mitigating it, with exception of just duplicating that whole circuit, and we can quickly experimentally verify that the system is still operational. Quite frankly, if you're going to start a 20-hour print, maybe take a couple seconds, unplug each thermocouple channel, and make sure the monitor still works. Maybe make sure the printer is still operational, look over the wiring, make sure there's nothing loose. I mean, that's just common sense, right? That's just not being negligent. Not all risks need to be mitigated with hardware if it doesn't make sense. A maintenance or sustaining schedule is very important because over time, every system will fail. We can put 500 of these in series, but eventually, there will come a time where things progressively fail and the protection is eventually compromised. Failures in time are exactly that. We can make failures less likely or more likely to be safe. We can make failures more likely to be insignificant or not catastrophic, but eventually every circuit and design will fail. I think it's safe to say that in the case of our thermocouple monitor and comparators, failures in these devices is most likely immediately after manufacturing. This is commonly referred to as infant mortality, in other words, never working at all. Using 2 Seths to watch the same printer redundantly reduces the probability of failure even further to a level that I believe is truly negligible. I'd be surprised to see a dangerous catastrophic failure in a single Seth system with an occurrence rate higher than 1 every million hours after the first 100. With 2 redundant Seths, I bet this would drop down to less than 1 dangerous catastrophic failure in less than 1 out of every 100 billion hours. Nuisance trip rate, to be determined. Speaking of, bit of a tangent, but there's a problem with just ripping the power cord out of 3D printers. See, they have this very important hot end cooling fan that prevents heat creep from clogging the nozzle, and just pulling power from that cooling fan without letting the nozzle cool first will be a bad time. That's why I added an auxiliary 12-volt output from this printer. In retrospect, perhaps I should have modified this design so that 12 volts can be output either when the relays are on or when the relays are off. Yeah, that jumper would have been really nice. I should really add that in Rev B, but right now, this can be used as a control signal to turn the fan on from an auxiliary power source. It's just 12 volts when the printer is on, and 0 volts when the printer is off. Which isn't directly useful for powering the fan. Totally didn't whiff on that. Nope. This is as intended, for sure. There are a couple more failures we need to cover. Failures of the 5-volt regulator outright will never turn on the BJTs and therefore never turn on the relays. A power failure in the 12-volt power brick will remove power from the relay coils, causing them to turn off the printer, which leads us straight to the most likely nuisance trips. We're using relay coils that are being held on all the time. That's not necessarily what they're designed for. Latching relays are typically used for this type of application, but I couldn't guarantee that a latching relay could be reliably unlatched in the event of a power failure without a significantly more complex, which means expensive, circuit. If the relay is set to on and 12 volts is removed before the logic circuit can unlatch that relay, protection has been compromised. I added a series pass element that's a 0 ohm for now, which will allow for tuning the quantity of power required to latch and hold that relay on, which can then be optimized to reduce the quantity of power dissipated in the relay coil, which will extend its life. Eventually, I expect the relay coil will wear out, and this failure will cause the relay to turn off, disabling the printer. Between the 12-volt power brick failing and the relay coil, I think those are the two most likely sources of nuisance trips. I feel like we're running on overtime, but I also feel like we need to talk through a couple more points, so hang in there. This temperature monitor is relatively complex, and there's a very simple way to drastically improve the safety of your 3D printer right now with two components. A non-resettable thermal fuse is a great way to set a hard thermal limit. They're a great way to enforce an absolute temperature cutoff that effectively does the same thing as Seth. There aren't a whole lot of these rated to break DC, so that might be an issue if you try to find one, but basically these devices function by using something which physically changes position, like a switch, at a specific temperature. Some thermal cutouts are made to open permanently, and others are made to be self-resetting, but thermal fuses are pretty foolproof. Like, they have safety agency ratings that say that they're pretty much guaranteed to open the circuit if the temperature threshold is exceeded. These are a great foolproof way to improve safety of anything powered by mains that should be temperature limited. If I'm being honest, a thermal fuse may prove to be a better solution than Seth, though the convenience of an adjustable trip threshold is not lost on me. If you're not interested in adding a thermal monitor to your 3D printer, but want to add an extra layer of protection, consider a thermal fuse. As long as you're using AC-rated fuses for AC and DC-rated fuses for DC, a thermal fuse with an appropriate certification from UL should get the job done just fine. I dropped a link to an AC-rated thermal fuse product family in the description, so check that out if you've never heard about a thermal fuse before and want to learn more. This design, like all designs, needed to make some trade-offs. For example, we needed to balance cost and fault tolerance. Another example is how we needed to balance safety and the lifetime, or how long this device will last. Using a latching style relay would have likely resulted in a longer operational lifetime, but that also means that it would be more likely that the system could fail into an unsafe state. What does that mean? Well, either unplug or trip this thermal monitor when it's not in use, which will de-energize the relay coils and cut power to the printer, significantly minimizing the reduction in design life. In most designs, compromise needs to happen, and I believe this design is a good balance between safety, reliability, and cost. I don't think it's terribly difficult to build a device that fails predictably into a safe state, or where the most probable failure is inherently safe. It's just about decisions. For example, we could have chosen to use a normally closed relay contact, but then Seth would stop protecting the printer from thermal runaway in a power failure condition. That's why we took the time to think about this design and categorize faults as either low risk, which is a fault that has no impact to safety, or unacceptable faults. Some of these unacceptable faults or failures were prevented through circuitry that now appears in the design, and other faults were prevented through LED indicators and a regular inspection schedule. That said, I don't believe there's any unsafe failures in the circuit that aren't adequately mitigated through occasional performance testing and inspection of the system. Now that's easy to say, but if you want to see the proof, then stick around, get subscribed. We'll be doing some performance testing of this design very soon. Don't miss it. That's all I have for today, but if you like this video and can't wait for more, let me know by getting subscribed, hitting that like button, and leaving a comment down below. Coming up next, we'll make sure this temperature monitor resets correctly when plugged in and discuss our physical implementation of this design. Really important stuff. I can't wait. If you want to support the channel, consider checking out the products that we feature today through our Amazon affiliate links in the video description. Really helps us out a lot. Thank you. Most of all, I hope that you learned something great today, and I hope to see you again soon. So thanks for watching EE for Everyone, and thank you for staying till the end. Bye!